Okay, let's get started with our 5 o'clock press conference. This is on Dawn's new views of asteroid Vesta. And we have 3 speakers who are going to speak in this order. Vishnu Reddy, he's Dawn Mission Associate at the Max-Planck Institute for the Solar System at Katlenburg-Lindau, Germany. And he's also at the University of North Dakota in Grand Forks. Our second speaker is Eleonora Ammannito. She's Visible and Infrared Spectrometer Team Associate. She's with the National Institute for Astrophysics in Rome, Italy. And our third speaker is David Williams. He's Dawn Participating Scientist and Faculty Research Associate at the School of Earth and Space Exploration at Arizona State University in Tempe, Arizona. And we also have here in the front row, Carol Raymond. She's Dawn Mission Deputy Principal Investigator. She's with the Jet Propulsion Laboratory in Pasadena. She'll be available also to answer questions.
Okay. Good afternoon. My name is Vishnu Reddy. I'm a member of the Dawn framing camera team from the Max-Planck Institute for Solar System Research in Germany, which contributed to the framing camera. Today I'm going to talk about framing camera color observations of Vesta, the remnant protoplanet, which is the first target of the Dawn mission. Okay? The color images obtained by the framing camera have shown that Vesta is one of the most colorful objects in the solar system that we have visited so far. When I say this, the take-home message is that Vesta is unlike any other asteroid we have visited so far. So there's nothing in the asteroid belt that you can actually compare directly to Vesta that we have known till now. If you go to the first view graph, this shows Vesta from a different perspective than what we have seen so far. Here is a polar stereographic view of the South Pole centered around the Rio Silvia Basin. Let me get the laser pointer. So here you can see the central region has been omitted because of higher phase angles. So we don't have good corrections over there. But here you can see the region around the Rio Silvia Basin that shows the green colors centered on the Rio Silvia Basin. Here what we see is that the Rio Silvia Basin, which is about 290 miles across, and which is roughly about 466 kilometers. And the impact basin has a height of about roughly 76,000 feet, which is about 2,300 meters, 20,000 meters. Okay, in comparison, Mount Everest is only about 29,000 feet, which is about 8,800 meters. Like I said, the black circle in the middle is of data that has been omitted due to low illumination. This mosaic was assembled using the approach phase images at a resolution of about 1,600 feet per pixel. The colors here we see have been assigned scientifically to reveal the composition. For example, the red color you see is a ratio of 2 different filters, which is the 750 nanometer filter to that of 440 nanometer filter. The green color you see is a ratio of 750 nanometer filter to that of the 920 nanometer filter. And the blue color you see is the inverse of the red, which is basically a ratio of the 440 nanometer filter to that of the 750 nanometer filters. So what the colors say is basically that when you have greener regions, these have deeper absorption bands due to the mineral pyroxene. There are several reasons why they are deeper. We're still investigating that, and some of those results will be presented tomorrow in the scientific sessions. The red regions have the regions which have steeper visible spectral slope. This visible spectral slope could tell something about the rock types we are looking at. Also, it could be due to some other factors that are affecting the surface, either due to space weathering or something else. We're still not sure yet. We're still investigating it. And the blue regions are regions that have shallower spectral slope compared to the red regions. You can go to the next slide. The second view graph shows some close-ups, okay, of features. Here what you see is the Opia crater. This crater is approximately, I think, 33 kilometers across. On the left you see the images in the near-infrared bands. Here the red is about 750 nanometers. The green is 920, and the blue is 980 nanometers. So here, individual filters are actually assigned RGB, whereas this image actually shows the colors as color ratios of different filters. So these are same like the first image I showed. What you can see here is that this particular Opia crater has an ejecta blanket that spreads much south of this that is red in color. We're still investigating the true nature of this. Again, fresh impact craters, you can show them exposing material that has deeper absorption bands than material that is older. The next slide, please. Okay, here what you see is an impact crater close to the Rio Silvia Basin. Again, what you see is the near-infrared image on the left side and the color ratio image on the right side. One of the interesting features you see here is this mass wasting, either due to the impact of this crater, where you see material flowing into the other crater here. So you can see the mass wasting pushing material into it, into the fresher crater right here. So the main thing, what we're seeing on Vesta is that Vesta is covered with a lot of regolith, and a lot of regolith processing are affecting the colors that we are seeing on Vesta. So with that, I would like to introduce my next speaker, Eleonora, who's from the VIR team, to come and talk about the spectrometer results.
Thank you, Vishnu. I'm Eleonora Ammannito. I'm a VIR team associate. VIR, which is the acronym for Visible and Infrared Mapping Spectrometer, was provided by ASI, the Italian Space Agency, and is managed by INAF, the Italian National Institute for Astrophysics, and in collaboration with Selex Galileo, where the experiment was built. After the successful completion of the survey orbit, VIR operated during the high-altitude orbit, acquiring more than 4.6 million of spectra in the visual and infrared spectral range at the nominal VIR spatial sampling for HAM orbit, which is 170 meters. In the first panel, there is a distribution on the Vesta surface of the VIR data acquired during HAMO. This is an orthographic projection centered in minus 45 degrees. So basically what you see is the southern hemisphere. The northern hemisphere was not too much observed because it was not illuminated. And so most of the observations were on the southern hemisphere. And, but for the illuminated portion of the surface, it was uniformly observed by VIR, both in latitude and longitude. So we have a global view of the illuminated portion. So for the illuminated portion, we have a global view of the spectral properties of the Vesta surface. In the second, yeah, if you can go to the previous one, there is a red. So here there is a red rectangular, and in the next slide there is an enlargement of this rectangular. Okay. So in this figure, VIR data were projected on top of a framing camera image of the same region, which was acquired during the survey phase. In this view, it is enhanced the capability of VIR to detect the topographic details at a low scale, allowing detailed studies on the composition of different portions of the same feature. A quick look of data from HAMO confirms the result from survey. Vesta is characterized by a basaltic surface, and its spectrum is dominated by the two prominent absorption bands of pyroxene. This basaltic surface shows strong correlation between geology and mineralogy. VIR is an experiment built to study the mineralogical properties of the surface of Vesta. However, when mineralogical investigations are combined with morphology and topography, it is possible to get additional information. And in the next panel, there is an example of how infer the composition of deeper layers with respect to the surface, looking, for instance, inside the craters. In this slide, it is shown a representation of the snowman craters in the Marcia Quadrangle, located slightly north of the equator. This region is characterized by complex geology and topography, with craters of different sizes that are superimposed and interlaced. The black and white image on top left of this slide is a view at 550 nanometers. So, this one. A way to enhance the complexity of this region is to visualize the 1 micron pyroxene band depth, the distribution of the 1 micron band depth overlaid on the topographic elevation. In this figure, the vertical axis, and I'm referring to this one now, the vertical axis represents the elevation, while the colors give the indication of the band depth values. The green is representing a shallow band, while the red is a deeper band. Band depths are indicators of the mineralogy of the material, providing information on the quantity of pyroxene present. They are also indicators of the material physical characteristics, like grain size. Band depths are not uniformly distributed, but follow the geological structure, being more evident in one of the two craters. Out of the craters, the band depths are shallower. So you see here, more or less, where we have the green, while deeper band depth in red are concentrated on crater streams. And here, for instance, is pretty much clear. And that suggests that the impacts excavated different or fresher materials. Also, the stronger band depths are found in one of the two craters. So you see this one is redder than the other one. And, and this one is the one located on the lower topographic level. This behavior indicates that the impact excavated deeper layers, exposing materials with stronger pyroxene bands. The information we are getting about Vesta mineralogy tells us that Vesta is a small world with a complex geological history and evolution. And Veer, together with the other payload from the Dawn mission, is contributing to discover. And now I turn over to my colleague David Williams, who will discuss geologic features identified from the mapping of Vesta. Thank you.
Thank you, Eleonora. My name is Dave Williams. I'm a participating scientist on the Dawn mission, and I'm at the School of Earth and Space Exploration at Arizona State University. We have used framing camera images from Dawn's survey orbit with a spatial resolution of about 250 meters per pixel to map the surface of Vesta in order to identify the global diversity of geologic materials and structures. And I will use this shape model here to demonstrate that we basically, from a morphological perspective and at the global scale, Vesta can be divided into 3 regions. This is the South Pole here, which has the South Polar Impact Basin and related features, which we call the Rhea Silvia Formation. This unit is relatively lightly cratered. Next, we have the equatorial cratered and trough terrain, which is relatively moderately cratered. And then we have the northern cratered and trough terrain. This is the most heavily cratered part of Vesta. Although it is relatively incompletely imaged thus far in the mission, we've only been able to image up to about 45 degrees north latitude. The rest will be filled in later. So I'll hand this down here if the press would like to take a look at the shape model. The South Polar Impact is the bottom, so that's down and when you hold the model. We have continued our analysis using framing camera images from the Dawn's high altitude mapping orbit with a spatial resolution of about 70 meters per pixel to characterize examples of Vesta's geologic materials and structures in order to determine the possible geologic processes that produced them. The main point I'd like for you to take away from this is that Vesta is clearly a transitional body between small asteroids and larger planets. We have found a wide variety of surface features on Vesta: dark and bright-rayed craters, extensive systems of grooves and troughs, scarps, slumps, partially degraded impact craters that have been modified by mass movements, and even possible evidence of impact melts. But we were surprised by the quantity and the scale of many of these features, and I will show examples of several of them. May I have the first graphic, please? Okay, what you see here is a mosaic of 3 framing camera images from the high altitude mapping orbit, And we see here an impact crater that is 28 kilometers in the north-south direction by 33 kilometers in the east-west direction, and it contains a 22-kilometer diameter deposit of slumped material in its interior, and also a 35-kilometer long flow, most likely an ejectalobe, that's been in place downslope from the western rim of this crater. It is flowing downhill into this depression right here. The eastern rim on this side is higher than the western rim, and the overall topography is downhill as you go from east to west in this mosaic. The relatively undisrupted form of the deposit in the crater suggests that it is a rotational slump rather than, say, a landslide that's been caused by shaking from an impact. We are finding a great number of examples across Vesta of impact craters that have been disturbed by deposits of mass movement downslope. The widespread, very steep slopes across Vesta, combined with the extensive regolith of loose material from impact cratering, makes Vesta's surface very conducive to flow by gravity-driven mass movements. In other words, the steep slopes and the loose regolith make it very easy for slumps and landslides to form on Vesta, even in its relatively low gravity. May I have the next image, please? Here's an example of a bright rayed impact crater right here that is 3.5 kilometers in diameter, and it is located on the rim of this older crater here named Tuscia, which is located in the southern hemisphere of Vesta. The local topography slopes downhill to the southwest. There are about a half dozen of these bright rayed craters and several dark rayed craters that are visible at the global scale, and many more that are visible at higher resolution. There are also ejectablankets of distinct colors around two large impact craters, which you might have noticed in the images that Vishnu showed at the beginning. These colors are distinctive relative to the average Vesta surface. These variations suggest that there are compositional differences in either the impactors that struck Vesta or in the target rocks at different locations on Vesta. And understanding these compositional differences are one of the things we want to investigate with VIR and GRAND data over the course of the next year. May I have the next, please? Okay, what you see here is an animation produced by my colleague David O'Brien from the Planetary Science Institute, which shows a framing camera image superposed on the digital terrain model of Vesta, and it shows an unusual hill right over here, containing a dark rayed impact crater and nearby dark deposits. And as it comes around, you can see the dark rayed crater is right here, and you can see the rays coming off of it. And then the crater's right here with the dark rays. And then over here, this has a dark deposit on it. The hill is 42.5 kilometers long by 28 kilometers in width and appears to have been sculpted by impact craters. The dark deposits on this hill were first visible in the approach images and first suggested that the hill was a possible volcano, but the lack of any clear evidence of extrusive volcanic features on the hill suggests that it is more likely a linear volcanic dike or a magmatic intrusion that is being exposed and eroded by impact craters. A key test of this will be to determine if there are any compositional differences in the dark material exposed by the dark rayed crater versus the dark material on the northwestern slope of the hill. Thus far, there is no unambiguous evidence of volcanic materials identified on Vesta in contrast to models and expectations. The search for these materials will continue as we look at the higher resolution data and as we start applying other techniques, for example, spectroscopic analyses. The main point I'd like you to walk away with is that although many of these surface features were seen on other smaller asteroids, we were surprised by the unexpected nature of these features on Vesta, particularly the extent of the brightness and color differences on the surface, and the degree and larger size scale of many of the morphological features, particularly the mass movements. Vesta is clearly a transitional object between small asteroids and planets, and is unique in many ways. And we'd now like to open the floor to questions. Thank you.
Hello. Okay. Before we get started with questions, I just want to mention that a link to the images for any reporters who want to get them is available on the AGU website, on the fall meeting website under the Media Center. When you click on the Media Center link, go down the pull-down menu to Virtual Newsroom, and there's a link posted there. It's also posted on the chat on the web streaming page. Okay, so let's get started with questions. Harvey, and then Rick.
Rick Lovett, freelance. Dr. Williams got to this toward the end here, but I would like a more general explanation for how all of these features come together in our understanding of what Vesta is and what makes it different from being an oversized rock like the others that we've seen. So I'm looking for the cool bottom lines in what we've had a lot of details in.
This one here. Sure. Yes, this is Dave Williams. I would say that the processes we're seeing are much more planet-like than what we would have expected. The degree which we're seeing features particularly the mass movements, the wide degree of color variations, were things that we did not expect from the studies of smaller asteroids. The size of these features, the scarps that we're seeing, the degree of degradation of the surface, I would say. That to me is a big surprise to see on a body like this, that we have not seen on smaller asteroids.
If I can follow up on that, what in your definition is planet-like as opposed to asteroid-like? I mean, you're describing features. I'm kind of more interested in what it means about what this world is, both its interior and its totality.
In its totality, this body has been very heavily influenced by impact cratering, particularly the formation of the large basin at the South Pole, and its features on the surface are very a response to that. And we haven't seen things quite like this on other asteroids. The degradation of the surface, the mass movement features in particular, are the sizes of them as well as the types are something that I don't think we've seen on smaller asteroids before. And Carol or my other colleagues can chime in on this as well.
Yeah, no, the main thing is that Vesta is differentiated. We know it from the meteorites, and we have a link between the meteorites and Vesta using spectroscopy, which Eleonora showed. So unlike the other objects that we have visited so far, be it Eros or Itokawa, those are mostly very small objects that have been fractured and reaccreted, and they're mostly homogeneous. Okay, one of the distinct things, you have to come to my talk tomorrow, but one of the things we notice is that way before even Don got there is that as Vesta rotates on its axis, we see color variations on the surface that's unlike any other object that we've visited so far. There's no asteroid that is like Vesta in the asteroid belt. So which brings up the question, what is that? When you try to do planetary geology, one of the simplest tools we use is comparison with other objects that we've been there. So is there any other asteroid in the asteroid belt that we can compare Vesta to? And the simple answer is no, at least so far. We might find something, we don't know that yet. But so far, the best analogy we found, the best examples we found are more in the terrestrial planetary side compared to the asteroid size, which are mostly rubble piles that have been reaccreted and are mostly homogeneous It's very rarely that we see actually rotational variation on any asteroid so far. I mean, I've studied thousands of asteroids with ground-based telescopes and even with spacecraft. So that's the reason why, we call it a transitionary object, because we don't see anything like it in the asteroid belt. So in a simple layman's term, you can say is that most asteroids looks like potato. Vesta is not a potato, so it's something else. What it is, we're trying to find out.
Harvey Leifert, a freelance writer. I'm a little confused about the whole color thing, which seems to be a very important part of this. The images that Dr. Reddy showed were in the infrared range, and then others that were manipulated by filters. And all the other ones we saw seemed to be gray to me. So I'm wondering, what are the real colors, and how can we see them?
Producing a real color image is a lot more difficult and tricky. One of the things we're interested in is what is the scientific information we can get out of these images. So just because something looks green doesn't mean it is a particular mineral. We have to try and quantify what it is. And so the best way to do that is actually taking ratios of two different filters. And what it tells us is that it not only tells us something is green, but it tells us how green it is and what are the likely causes for this color variation we see. And the best part about the Dawn mission is that we have instruments that are very complementary. The framing camera can see on a much better spatial scale, but in terms of spectral resolution, the spectrometer can do a much better job at it. So we can go ahead and identify large areas that are showing distinct color variation and say these areas look distinct either due to some surface processes or due to impacts or something endogenous that's from the inside. So then the spectrometer goes and actually probes and finds out what is the actual process that's happening in terms of composition and stuff like that. In terms of colors you saw today, the green color you saw, that's the main thing is that something is causing these absorption bands to change in depth. Okay, the absorption band is due to a mineral called pyroxene. It's one of the most common mineral that we find on terrestrial bodies. Something is causing this pyroxene band to change, and that's causing this intense green bands. And we see this intense green bands related to the Rhea Silvia structure. So it could be that we are excavating something that is deeper, that has a different composition, or it's something like this material is fresher than what is already been exposed earlier. So we're not sure yet. We're still trying to investigate whether this is an effect due to exposure to space weather, whether it's a compositional effect, whether it's a grain size effect. So we're still trying to quantify. So the main point is that we tell the spatial scale, and the spectrometer tells the compositional differences in much more spectral scale.
Hi, I'm Irene Klotz with Reuters and Discovery News. Aside from the pyroxene, can you give us kind of an ingredient list of what you think is on Vesta? And also, just to clarify the last question, to the human eye, would we see different colors if we were there and could look at it?
Okay, so you want an ingredient list and you want to see what a human eye would see. So I think yes, you can see color differences in human eye. You have to go to Dr. Keller's talk tomorrow. He has the best images that you can. What would we see? And it's not all gray. So the common saying that asteroids have painted themselves gray might not apply to Vesta actually, because we do see subtle differences in color. It's subtle, but it's not gray. Ingredient list. I'll let Eleonora, because she's the spectroscopy expert here. So I'll let her because she can tell it better than me.
Well, right now we have done an analysis on the approach and survey data. So the scale that we have analyzed so far is 100 meters, more or less. And at this scale, we are getting this general idea of basaltic crust with pyroxene everywhere, and we don't see, we see variation within the pyroxene family, because pyroxene is a very huge family of minerals, so they can change a little bit, but still being pyroxene. If something else is there, well, is mixed. We don't see at the 600 scale. We are analyzing right now data from HAMO, and in that case we are looking at 200 meters scale. And at that scale, it's possible that we will see something different from pyroxene, but we are still analyzing data, so I don't have, I don't know. You stay tuned, and you will know later on.
I have a question from Robert Zimmerman from BehindTheLive.com. His question is, does anyone yet have any theories as to what caused the asteroid's 3 different regions, and were they formed as separate objects that crashed and fused together?
In regard to the 3 regions, obviously the southern region was affected by a large impact. It is a large impact basin down there. That's the least cratered part of Vesta, and we see progressively heavier cratering as we go from south to north. As far as what processes have made the other parts of the surface, we see lots of impact craters all over the place, and we see these unusual troughs, flat-forward troughs that have go around the equator in the the equatorial region of Vesta. But we also see some troughs in the northern hemisphere that have a different orientation, and the details about that are going to be given in talks tomorrow by Paul Schenk and Deborah Buchkowski. But those tectonic features, we think, in some way are related to the formation of large impact basins on the surface.
Hi, Emily Lakdawala from the Planetary Society. I'm interested in the yellow areas on your ratio maps. I know that red usually means old and weathered, and deep pyroxene absorption bands usually means freshly exposed. So I'm intrigued by. I mean, do you have any speculation as to what those areas mean compositionally?
Like yellow areas?
Yes, the yellow. So they're both red and green.
It's intermediate. It's the simplest explanation would be that,
Okay.
But compositionally, it's tricky in the sense that as much as we like to say Vesta is differentiated, like Dave pointed out, it's completely beat up. It's so beat up that, unlike the moon where you can see, large basins filled with lava flows, we don't see that on Vesta. So there's a lot of regular crossing. So whatever is there is completely mixed together. So that makes it much more interesting for us to use the framing camera color data to identify distinct units and then go with the Beer spectrometer to probe what these materials are. The main thing is to find a link between these colors and composition or surface processes. So yellow falls between, it's less green, I guess. So you can say it's a mixture of both. So beyond that, I don't think I want to speculate.
Do we have any other questions? Okay, we have and I'd just like to remind everybody again, please identify yourselves, including the people answering the questions.
If the dark rays from impact craters are not volcanic, what caused them?
That's a good question. We are in the process of trying to figure that out. But one idea is that you could have dark primitive meteorites, carbonaceous meteorites, that it could have impacted onto the surface and produced dark rayed craters. And that's one of the things we want to look into, is test that hypothesis over the course of the next year to see as we get the higher resolution spectral data, to see if there's any differences in the compositions of dark rayed craters versus some of the other darker materials, to see if there's something that would be more indicative of a carbonaceous meteorite versus something that's more of a basaltic composition.
So there's actually a task force that's been formed to study this, and at the Lunar and Planetary Science Conference we're going to present brand new results about that work.
Irene Klotz with Reuters and Discovery News. Is there any sign that that Vesta has a core, and will more info on that be coming? And also, this isn't observationally based, but what's the leading theories for what an object like this is doing in the asteroid belt, and why didn't it become a planet? Did it not have enough, similar bodies nearby to kind of meld together, or what's kind of the framework for thinking about the why this is so odd and unusually placed?
So the question is, why does Vesta have a core? And second one is that why is Vesta still hanging around in the asteroid belt, even despite being so big? The first answer is that tomorrow we'll have a talk where we will actually present results about whether Vesta has a core or not. So I think the speakers are in the audience, so you can get in touch with them tomorrow after their talks. As far as that would be Carol's. Yeah, the geophysics of dawn, I think. Yeah, of Vesta, sorry. Yeah, and as far as what's Vesta doing out there? Well, that's why we're there to investigate. So we don't know why. Why is that Vesta and Ceres are so special? You know, everything in the asteroid belt has been beat up so badly, and been catastrophically disrupted. So there's something special about it. If you look at the meteorites, we have about 102 to 120 objects that differentiated. We know this from basically the iron meteorites. So if you have an iron meteorite, the only way, most logical way to form an iron meteorite would be to differentiate an object, where you have crust, mantle, and the core. And the only way you can take this iron meteorite out of the core is to completely destroy it. We call it a super catastrophic disruption. And so we have so many different kinds of iron meteorites, they have to form distinct parent bodies. So how come these 100-odd bodies got disrupted, whereas we still have Vesta more or less intact? That is, we don't know the answer yet. So, so we're trying to find out why Vesta. I mean, it's not that Vesta is completely intact. If you look at the shape model, you guys had a chance to touch it. There were several large impacts, that have tried to disrupt Vesta. So we don't know whether the internal structure has something to do with the way Vesta is being protected and still intact today. We're not sure if it has something to do with Vesta's location. We have to realize that we have a family of objects called Vestoids that actually are pieces of Vesta that have come out probably from Vesta. So we know that some pieces of Vesta have been taken off Vesta. And the question is that why it remains intact. I don't know. We're still trying to find out. So.
I think we can also mention something else that's sort of unique about this particular mission, Dawn at Vesta. In most planetary explorations, we send a robotic spacecraft to a planetary body to gather its orbital data, and then eventually you progress to landers, and then in situ measurements, and then, if you're lucky, robotic sample return. With Dawn, we're going about it the opposite way because we already have the samples. We have the HED meteorites that have been very heavily studied in Earth laboratories. So we have information about aspects of it. And now, later, with the Dawn mission, we are actually doing the robotic reconnaissance of that body as from an orbit to determine the geology and the composition and the gravity and interior structure, and then relate that back. So that's one of the goals of this mission is to relate what we're get the information we get from the Dawn mission to the meteorites that have been studied in the laboratory and try and bring those two together to understand the evolution of Vesta.
Rick Lovett, freelance. Earlier you said you expected to see a volcano, and that the theory said there would be, but it didn't look like one. I'd like to know why theory, I got a hunch on some of this, but why the theory predicted a volcano and what absence of volcanic features on the surface would mean for our understanding of it if we don't find any.
That's a good question. There has been mathematical modeling work that was done based on some of the information from the HED meteorites, and this mathematical modeling suggested that there are certain types of volcanic materials we might have expected on Vesta. Lava flows of particular dimensions, small amounts of pyroclastic deposits that would have fed what we call lava fountains, specific features like that, dikes that it would be exposed at the surface. And in our initial reconnaissance, we haven't seen that. And that was perhaps the biggest surprise to me, that we didn't see anything, at least not yet. We're starting to see indications of dikes that might be, like the feature that I showed there, and perhaps others. So it's sort of something that we're just now beginning to see as we get the higher spatial resolution data. But yeah, the whole idea for volcanism was because it's a differentiated body, because it's a basaltic asteroid, the anticipation was that we would see features. And after having looked at the images, I think it's due to the intense bombardment that this object has undergone over the course of solar system history, that if the materials are there, they're very heavily masked. That's why we have to use other techniques to continue the search for them.
I had a follow-up, but I don't know anymore. You just answered it.
Hi, Nicola Jones here, freelance, but I'm here for nature. Just a quick question. It actually says in the press release that Vesta has an iron core, and that's attributed to Carol Raymond, so maybe she could address that question about whether it has a core and whether that isn't new information.
Yeah, we have the low-degree gravity field has been mapped during the survey phase and the HAMO phase, and the component of the gravity field which is related to the flattening of the shape and the rotational symmetry of the body indicates that the shape of Vesta is that the gravity of Vesta is not consistent with the body being a homogeneous density. So saying it otherwise, that the interior of Vesta isn't all made of the same stuff. And it requires moving some of that material to the core, the densest material, towards the center of the body in order to match the gravity field. So that's what will be presented tomorrow.
And does that tell us anything in particular about either how it formed or why it's still there, all these mysteries we're talking about how it's different from the other bodies?
Yes, that's the end state of planetary differentiation, which Vishnu was talking about. So it's likely that happening early in Vesta's history was one of the factors that allowed Vesta to survive the intense bombardment. But clearly, as Vishnu has already said, there were other objects. We don't know how big they were relative to Vesta, but some combination of the factors of the density or the strength of Vesta, the size of Vesta, and likely its place in the solar system, and perhaps just luck, may be the reasons that it's still around today.
Yeah, now just to add that now that Carol has let the rabbit out of the bag, I'll complete my quote. If all the asteroids look like potato, Vesta is most probably looking like an avocado. So you have, that's the analogy I used last week with school kids. If you have a differentiation, you have something very dense in the middle, a soft mushy mantle and a very thin crust. So that would be the best analogy if you want to put, it's not a potato, it's an avocado.
Do we have anybody on the phone who would like to ask a question? Okay. Anyone else in the room would like to ask a question?
Yeah.
And please identify yourself and also whoever answers.
Steve Conlon, The Independent. Just very quickly, how old is Vesta, do we think?
What's the age of Vesta?
Okay, any others?
Maybe Carol can answer it.
So the
No.
question was, I actually didn't hear it.
How old is Vesta? The question.
Okay. What's the age of Vesta? Okay. And yeah, I forgot to identify myself. I'm Carol Raymond. Carol Raymond. Oh, stop. The age of Vesta is essentially the age of the solar system. We believe it formed within the first few million years after the formation of the solar system. So, 4.565, something like that. And so the geologic age of Vesta is, of course, what we're after here, not the formation age, because there have been, as we're discussing today, lots of planetary processes that have occurred, the differentiation of the body, the battering of the surface, the surface modification processes, and so the creation of these global tectonic patterns that we see that Dave has explained, those are the things that we're trying to date, and so we can build up the geologic history of Vesta and understand how that what factors were important in shaping the body that we see today, and perhaps the reason that it's a surviving protoplanet.
Okay, we have time for one more question, if anyone here has one, or anyone on the phone. No more questions? Okay. Well then, thank you very much for your presentations, and thank you everyone for being here. This is our last press conference for the day. We'll start tomorrow morning